Let's begin. We'll finish up with nonlinear equations today. We'll solve a small system. In your homework assignment, if I finish by Thursday numerical integration, you will have a very interesting assignment where you're combining a nonlinear system with numerical integration, so that should spice things up a little bit. And then in your project, you will solve a very large nonlinear system of equations. So you have to figure out how to put all of the residual functions together. And this is actually an example of what you might see in your homework assignment. A material immersed in a radiation environment, like a skewer in an oven. Again, I take this one-dimensional piece of material, like the rod we solved. Last time we solved it subject to fixed temperatures at both ends, and there was a heat source over here. In this case, we have some radiation environment. These are the elements in your oven, and they're radiating heat throughout the oven. And this radiation is hitting the skewer. Imagine there's meat or kebab here, or kafta or whatever. And the equation that governs the temperature distribution inside the material or the skewer looks like this. It's the same second derivative. So pay attention to this. This second derivative represents what we will call diffusion later. Diffusion, heat transfer is a kind of diffusion. Mass transfer is a type of diffusion process. So they will all be represented by second derivatives. So the temperature changes in a diffusion type mechanism, which is at the molecular level where molecules are communicating information to each other at the molecular level. And on the right-hand side, you have this highly nonlinear term in temperature, T to the power 4. That's a property of radiation. T infinity is the surrounding temperature of the material. That's known typically, let's say, when you're broiling in your oven, that's 500 or 550 Fahrenheit. That would be T infinity. It's a known quantity, also to the power 4, but it doesn't matter. It's a known number. But this T to the power 4 is highly nonlinear, because here you have temperature, your dependent variable, and T shows up highly nonlinearly in this system. And we convert this like we did with the other problem. We convert the differential term into an algebraic term. And then you get an equation that looks like this at any one of these points on the interior. Again, you will do something like this for your project. So you're fairly familiar right now with this procedure, how to put these equations at every point. Except now that these equations are nonlinear. Ti plus 1 shows up linearly here. Ti shows up nonlinearly, and Ti minus 1 shows up linearly. So this is just the fact that there's one of them with a nonlinear term. It means this is going to be a system of nonlinear equations. And then you put all of these equations together at all points, you have a very large system of nonlinear equations that you have to solve together. Now, what does that mean for a single equation? We saw that to solve an equation f of x equals 0, you're intersecting that f of x with the line y equals 0, correct? But when you have two or more equations, it's not that obvious. In fact, it's practically impossible to visualize, except in very, very limited cases where you can separate the y values from the x values nicely. Like in this example, these are two equations where I could separate y as a function of x, so I can plot it on a xy plot. This is just a unique setup. If I had log y over here, cosine y squared, etc., it'd be very complicated to try to plot this. But this is the only situation where you can actually plot and visualize this, although the answer is, the conclusion we will reach is the same for any large system of equations. What do we mean when we say we are solving these equations simultaneously together? It means we are trying to find those points where those curves intersect each other, okay? Where those curves intersect each other, where they touch each other. In this case, there are going to be these yellow points over here. So this is going to be the working example we're going to work with, just to show you, to illustrate to you how we will find the roots. You still call them the roots, how we will find the roots of this system, or the points of intersection. We're going to hit them one point at a time, because the method we use cannot find all the roots for you. It can only find one root at a time. Your initial guess has to be close to the root that you want to find. Now, as usual, we also write these equations in residual form. You move everything either to the left-hand side or to the right-hand side, and you define these new residual functions. We're going to call them now R1, R2, R3. If you have 50 equations, you have 50 residuals. If you have 1,000, you're going to have 1,000 residual functions. But we put everything on the left-hand side or on the right-hand side, whichever you prefer, because those are going to be equal to 0, set to be equal to 0 eventually. So solving this system now means finding x and y such that both the residual functions are equal to 0, and they are both essentially hitting, in this case, the y equals 0 axis, but in the general case, just the point where all of them are equal to 0. The method we use, which is based on Newton's method, can be extended to solve a system of nonlinear equations. I'm not going to go through Newton's method. This is not the objective of this course. If you want to learn it, you can look at my lectures in numerical methods. But what I want to remind you of or pass on to you is how to solve this in Python. Again, these are things that you might face in your PhD research. You don't have to remember this, but you have to remember that, yes, I know how to solve a system of nonlinear equations. Let me pull up my notes. That is sufficient for you to recognize. But if you look at this and you're like, yeah, how do I solve this? I don't know. Then you are in trouble. If you know that if you can identify this is a system of nonlinear equations, we did cover this in foundations. So I'm just going to go back and remember what we did. That is going to be sufficient. Okay. All right. So let's formalize this first. In general, an arbitrary system of nonlinear equations will be written in this form. A bunch of residual functions, R1 to Rn or R0 to Rn, however you want to number them. But you have to assume that each residual is a function of all of the variables of interest. We're trying to find the roots, x1, x2, etc., xn. You need to have as many residual functions, as many residuals, as there are unknowns or roots that you're trying to find. Okay? Our variables of interest are given by this solution vector that we're going to put in an array or a vector x, and that's going to contain x1, x2, etc., all of the roots. And we can therefore also form a vector of residuals. And you will see in Python, we're going to fill in a NumPy array with residual 1. That is a function of all the x's. Residual 2, that's a function of all of the x's, and so on and so forth. So in the previous example, I had x and y. Those should be called x1, x2, okay, in this pattern. Okay. You can use the root functionality from SciPy the same way we used it to solve a system, a single equation with a single unknown. You can use it to solve any size system of nonlinear equations. Okay, well, now, whether there's a guarantee you're going to find a root or not, that's a different question. We're not asking that question because that is going to depend on whether there is actually a root in the system, and if there is a root, how close is your initial guess to it? Because nonlinear solvers are very complex, they complicated, they might not necessarily guarantee convergence. If it doesn't converge, you don't give up, you try a different initial guess. Okay, and that's where your expertise is going to come in. So the way we will do this is we will define a Python routine to compute all of these residuals or this residual vector, and we will put them in a NumPy array. Okay, and you are going to assume that this vector of residuals is a function of all of your variables of interest, the ones that you're interested in solving. Those are going to be the argument, as the argument. You will assume that, just like we did for the single variable, we defined our residual function or residual routine. Its first argument was the variable of interest. In this case, you're defining a residual vector. Its first argument is going to be the vector of variables of interest, this guy. Right? So analogy, going from a scalar to an array I use vector loosely here as an array. This is not a vector in the traditional sense in math. Yeah. Now the routine is going to return an array of residuals ordered in whatever form you want to order them, but you have to stick to that order. Once you determine an order, stick to it. So for example, I'll give the example and we can jump on Jupyter Notebook and implement it together. So for example, for this system of equations, my two residuals were 1 over 2x cubed plus y minus 4x, etc., etc. This is how I would define my residual vector. Let me discuss it for a second, and then we will implement it together. I'm going to define a routine called residual, and I'm going to assume it takes an array of solution of the solution vector or the solution array. I call it vars. Now, in my convention here, I'm going to refer to whatever goes in the first entry in vars is going to be my x value, and in this system, so this is var 0 is going to respond to x, and vars 1 is going to correspond to y. Can I change? Absolutely. But then you would have to change your initial guesses in your root function. So you have to be consistent. Whatever you call, if the first entry in your solution vector, you refer to it as this x, then you have to stick to that convention throughout all your code. You can swap them however you like, but you have to be consistent across. Okay? So I'm going to refer to whatever is contained in the first entry of this array is going to be my x, and whatever is contained in the second entry is going to be my y value. Now I have x and y, and I simply implement this. R1 is simply going to be a number, 0.5 times x cubed plus y minus 4x, and R2 is y minus sine x e to the minus x. Now, why is this a number? Because when Python, when the routine calls residual, it's going to pass on actual numerical values here. The code is going to take these values, plug them in here, and return numbers. Okay? And then Python is going to check, am I close? Is R1 close to 0? Is R2 close to 0? If not, continue. Continue the procedure until we get them all close to 0. Okay? So you define your residuals. In this case, it's simple. You just have two residuals, R1 and R2. And you return is simply a NumPy array that contains R1 and R2, again, in the order you have chosen. Okay, so you have to be consistent across. If you decide this is my R1, this is my R2, that's what you are going to return. Okay? Because then the return value of your roots is going to be, however you chose this, x and y or y and x, those are going to be your roots. All right? Let's go next, and then we'll implement everything in Python in the Jupyter Notebook. Finally, you just simply call your root with your residual and initial guess. Now you have a vector. Okay, I'm going to call root residual vector, so that is going to be residual or my residual, whatever you call this. It's the name of this routine. And instead of having a single initial guess, now you have an array of initial guesses, a vector of initial guesses. So for example, in this case, I'm calling root residual, comma, my first initial guess for x is -2, and the initial guess for y is -1. Okay, very simply. So what am I trying, which root am I trying to find here for this example? I'm going to try to find this root. So I gave it -1 for y, okay, and -2 for x. So I gave it these two. I put my initial guess over here. And I'm hoping it's going to try to find its way over here. Pretty close. Okay? So let's do this together in class. Get your Jupyter notebooks up and running. And in your project, you're going to have to do a system of an arbitrary size with that radiation problem. So you cannot hard code R1, R2, R100, or R1000. You have to find a programmatic way to put them all into one residual vector. All right? Let's get to our Jupyter. Okay. Of course. Give me a moment, please. It's my wasp sting. It's making me slow today. All right. All right, so I'm going to create a new notebook here. New notebook. And I'm going to move it. I can see. How did I do this last time? Did I sit over here? Maybe I should sit over here. All right, sorry, I have my back turned to you. It's not on purpose. Okay. So, fall 2025 in class non-linear system example. And again, I'm going to grab my boilerplate. Where is my boilerplate? Going to grab my boilerplate. Now we're going to add something to the boilerplate, which is the root. Well, actually, we added it last time. Nope, we didn't. So from scipy.optimize import root. Okay, you guys in the back can see? Yep. Okay. So I'm going to define, I said my residual, my residual function or my residuals. Okay. I'm going to say define or def my residuals. Call it residuals if you want. And vars. Give it vars. I'm assuming vars. I'm going to assume that this is going to be an a numpy array, an array, and x is vars 0, and y is vars 1. Then r1 is 0.5 times x cubed. So let me separate for readability. Plus y minus 4x. You don't have to put the decimals, but it helps. And then for the second residual is y minus mp.sin x times mp.exp of minus x. Let me double check that I got these right. Yep. Y minus sin x e to the minus x. So I got these two. That's it. That's my my residual routine, and then I'm going to return a numpy array containing these two residuals in this order, R1 and R2. Okay? So that's define my residuals. Next, let's think about which root we want to find. Now, we were lucky here because we can visualize this and we can be picky about which root we want. Again, in practice, you would know where you should be at. Like going back to the heat transfer problem, a good initial guess is either the average temperature between the endpoints, or you can do initial guess of a straight line, where, because we know the solution for this straight line in temperatures from T1 to T2 is when there's no source terms, like we discussed last time. We had the homogeneous situation. Okay, so you will know, it's like one of those wisdom things from, you know, the Lord of the Rings. You will know. I was like, oh, you will know, okay? All right, so let's say we want to find this root over here. Visually, this is located at x between -1 and -2, so maybe -1.5. And then for the y, it's going to be maybe minus 4.2 or something. So we'll start at -2 for x -1 and for y -2. So let's do root. And I'm going to give it my residuals. That's it, my residuals. And then it asks for the x0. And you can say x0 is equal to, we said -1 and -2, correct? And then when you produce the solution, it's going to give you a bunch of information here. Your solution dot x is going to contain the roots. The first root is -1.46, and the second root is -4.28. Okay? If you swap these over here, then these would be swapped as well. Just make sure that you are consistent, you know the interpretation. You can't interpret this as the root for y and this is as the root of x. That's not correct because these are in the same order you chose here. You choose that order. Okay? You choose that order. We can find another root. I'll give you a minute to catch up. 30 seconds. This is a silly little example. It's not a big problem, correct? The serious problems will be in the homework and the project. Okay? The more serious ones, and in your research. Now, in your research, you might have a couple of equations only, and those can still be very difficult to solve. So I'll tell you a true story. Last week, a faculty contacted me from the University of Florida, or Florida International University, and he's in business, and they're trying to do some data fit for revenue distribution of companies, etc. So we had a great discussion. The data fit required fitting a system of nonlinear equations, which was pretty complicated. It had summations and integrals and derivatives, a bunch of very, very nasty thing. But it was doable. But figuring out the roots, I had to leverage his knowledge, his expertise. Like, where do you think the parameters for this function are going to be? And so you will know. Okay? And although the system was like 4 equations with 4 unknowns, it was a very complex one to implement. Okay, so let's find another root. Let's say I want to find this one over here. So I can give it, for x, I can give it maybe 4, and for y, I can give it 1. So if I give it 4 and 1, please work, please work. 4 and 1. Oh, look at that. It found 2.8 for x. Okay, where is it? Yep, right here. 2.8 for x, and just about 0.01 for y. Okay, so it can find the roots for a system of equations. Now, that's it. That's it for the tool of solving nonlinear equations. Whether you do it for one equation or a system, root is the way to go. And with this, I'll be done with the unit on solving algebraic equations. The next unit is going to be on curve fitting, and I hope by Thursday we will be done also with some numerical calculus. So let me introduce the discussion on curve fitting first. And the animations might not be perfect. So it's putting those together rather quickly. Okay, so this next unit, I wasn't going to cover this, but then there was a question in the problem, and I thought it would be really cool to ask you to do it. Trying to fit the thermal conductivity from experimental data to use in the numerical calculator. Like, okay, this is a great example, but we need to look at curve fitting just in case you haven't seen it before. Besides, that would be useful for you if you're doing experimental work, you're obtaining experimental data, you want to do some interpolation or you do some regression. So it will be useful to remind you of that. There are 2 types of curve fitting that I like to discuss. Benign interpolation and fancy regression. And I'm giving here 4 examples, 2 of each, where that will guide your choice in whether you should choose interpolation versus regression. Interpolation is when your data is clean looking. In other words, there's a direct one-to-one connection, and there's between the x values, the independent variable, and your y values. And this could apply also in 2 dimensions. You might have a very nice and smooth curve, one-to-one connection between the x-axis and the y-axis. You see here for every value of temperature, I have one and only one value for, so for every value of the hour of the day on the x-axis here, I have exactly one value of temperature. Okay, contrast that to the data here. For one value of the x-axis here, I have two values for y. Which one is it, right? So this kind of data tells you, when the data is nice and clean like this, this tells you this obeys a very clear physical process. This tells me that, yeah, the temperature is very strongly correlated with the hour, with the time of day based on solar radiation. And, you know, I'm measuring this at a single location at some home. And so, you know, data like this, you can fit it with what we call an interpolant. The purpose of the interpolant is what is the temperature between any of the two measured points. So let's say we measured at 8 a.m. and 10 a.m., but I want to know the temperature at 8:30. Okay, what do you do in that case? You can just interpolate. Okay, because the temperature at 8:30 is going to be somewhere between 72 and 79, unless there was a thunderstorm or a solar eclipse and your temperature dropped. You know, then this will not work, obviously. But in most cases like this, you just do what we call interpolation. Same here. I'm looking at density as a function of temperature, density of air as a function of temperature. And as the temperature drops, you know, the air becomes denser, all the way up to like 3.7 kilograms per cubic meter. And then as the temperature increases, you see this decay and very nice, clear set of points, and then you can use this just to fit an interpolant, to put an interpolant in here so that you can find the density at any temperature from all of this entire range of temperatures. Okay, so this is very clean, clear data. These kinds of data are suitable for interpolation. You don't need to do regression or anything like this. You can do regression, but it's not going to go through each and every point. Regression, on the other hand, is going to try to give you a formula for what the model of the data should be. A model is simply a way for us to understand reality. Okay, I'm going to model it as a straight line, or I'm going to model it as a quadratic. I mean, it's not exactly the truth, but it's something that, based on intuition and knowledge, it could do a good job. And you'll see that data, when data is scattered all over the place, you might have two or more values, y values for a single x value. This is, for example, actual data from a person's height as a function of their femur length. So this is the femur here, the bone in your thigh, and in this region, the length of your femur is predictive of your height. Because we grow, our femur has to sustain our height. So there's a very strong correlation between femur length and a person's height. That's often how they predict from cemeteries and where they're digging out skeletons. They can predict a person's height just from their femur based on data like this. But as you can imagine, there's a lot of variability, whether you were doing the keto diet or the whatever diet or the Mediterranean diet, your femur could be like much longer than, the height of someone who was just drinking milk, etc. So, there's variability. We're humans, we're different, there's all sorts of ethnicities and foods, etc. So you can imagine there's variability. For one femur length here, like this one, 45 centimeters, we found two persons, one with 170 centimeters, one about 167, okay? And so, there's, same here. For this femur length, there's two persons. So the data is scattered all over, but there is a trend. As femur length increases, on average, height increases as well, right? Regression captures that trend. Regression says, I don't care about the minutiae. Saying that exactly if a person's femur length is 45 centimeters, then their height is going to be 170 centimeters is wrong. Okay? You cannot interpret this with precision. You can interpret it statistically. And that's what regression is doing. It's statistically trying to find a model that captures the trend of the data. In this case, we want to put a straight line here. And the objective of regression is, what is the formula of this straight line? Now, to understand how this is done, again, you can go back to your textbooks or look at my numerical methods to derive all the equation. What this line is doing is trying to minimize the error or the distance from these points to the line. Because this line you can put it like this, or you can change the slope and the intercept, right? It's trying to find exactly what is the best combination of slope and intercept that minimizes the distance between the sum of all of the distances between these points and the line itself. So when we talk about regression, we're talking about finding the parameters or the coefficients of your model so that you have the best fit. Same here. This is other data. It's noisy data, but we can see that the trend is sinusoidal. So I'm trying to fit a sine or cosine function here with these data that are given to me in blue. So we will look at both as a reminder. Again, I'm not teaching you the theory here, just giving you the tools that this is what if you want the theory, you can look at my other videos. But again, this is just I expect you to know this, but if you haven't, this will be just a quick refresher on how to do it. We will start with interpolation, and by definition, as you can see from here also, notice that the interpolant goes by definition through each and every point of the original data. So if I were to develop an interpolant function or routine in Python and say, give me back the value at the original data point on the x, it's going to give you the original y value, because by definition, the interpolant has to go through each and every point of your input data. For regression, that's not the case. It hardly goes through any of the input data points because it's a model. It's trying to capture the trend of your data. We start with interpolation, and that's the definition. An interpolant must pass through each and every point of the input data. It's like what the scouts do with these nails, and then they put the ropes through each other. I don't know if you've seen that or what scouts I've been to, but like we used to do like this art. We would put nails on a piece of plywood, and we would connect them with twine. It was really cool to produce like certain shapes and art. So this is like it. It's like you have a bunch of nails over here and you're connecting them with twine. The simplest type of interpolant is interpolation to a straight line, where a straight line has two unknowns. So you need at least and at most 2 points to build a straight line. And with interpolation to a straight line, it can take an entire data set and take each pair of points and draw a straight line in between them. That's it. And then when you're going to ask the interpolant, what is the value over here, it will do interpolation on this straight line. It knows the slope and the intercept of this line. It can find any value in between. Same thing here, same thing here. There's a different straight line between each pair of points. There's no single straight line for the entire data. Okay, there's a different straight line between the 2 points. That's also what you see when you go and say plot and you do dash dot, for example. What it's doing, it's connecting the points with a straight line. That's it. That's why I tell you when you're plotting scattered data, don't connect them with lines, because that's not the true function that is representing the data. It's just simply doing a straight line between the points. It looks good though, but this is what it does. Now in Python, you can very easily do this on any at least two pair of data points or any large data set. And from NumPy, we already know NumPy, you grab something called interp. That's a very specific type of interpolant. It does 1D interpolation to a straight line. So this only works for 1D data x and y, not x, y, z, okay, or higher dimensions. This works only on one-dimensional data, and it does interpolation to a straight line. NumPy.interp takes at least 3 arguments and returns a value. For your arguments, forget about the first argument. The last 2 arguments, xi and yi, are your x input data and y input data. So I'm referring to input. So that would be, in this case, of the temperature and density. My xi would be the temperature values, all the discrete values of the temperature, and yi would be the discrete values of the density corresponding to those temperatures. Xe is where you want to interpolate the data to. Okay, so let's say I only have data that's given at these blue points. So my xi's are going to be like 100, 150, 200, etc. And I have only specific. What if I want to interpolate here at this point at 125.3? Yeah? That would be your XE, over here. YE is the value that is returned, the interpolated value at XE. Okay, so let's look at the density versus temperature data together. In your canvas, if you go under Files, there's a new folder called Data, and there's a subfolder in that called Interpolation. There's a subfolder in, no, it's the babushka folders. So there's a subfolder in that called Interpolation. So from that, grab the data file called temperature and temperature density data. Okay, let me just double check the name. It's called interpolation temp density data .txt. Okay, just a simple text file. We're going to import that into Python and work with those data. Do you all see it? Yeah, canvas. Mm-hmm. Yeah. .txt. So yeah, interpolation. Yeah, then dash temp density data.txt. Grab it and put it next to your notebook. Okay, so we can load it up directly. Right, so in the meantime, I'm going to create a new solving algebraic equations. I call this fall. Whoa. Fall 2025 in class interpolation temperature density data .ipynb, and let me get the boilerplate. Let's see if I paste. I got the boilerplate already. Import numpy np, etc. Okay, so then let me. All right, so if I look at the data, let's see, data or input data, I'm going to use this is the simplest way of importing data into Python. I'm not going to cover big data set importing. I do that in statistics, maybe next year. But I'm going to do very simple, lightweight importing of data. It's not very hard to import data in Python. There are different kinds of data types. I cannot cover all of those. But for any data type you're facing with, you can jump on GPT or Stack Overflow and say, how do I import CSV data? How do I import Excel data? How do I import Google Sheets data, etc.? So there's all sorts of ways to import data. Once you import the data, you can work with them with the tools that we've learned. I just need to do this here because I don't want to have you type in the temperature and density data. The simplest way we can import numerical data with Python and NumPy is through np.loadtxt. So it's just going to load a text, and for this one is going to be called interpolation temp density data.txt. And once I do this, I just press Shift Enter, and it does something. So when in doubt, print it out. So let's print input data. So okay, this data contains 2 columns. The first column corresponds to temperatures. So 100, 150, 200, all the way to 1,000, 10 to the power 3. And then the density values, 3.55, all the way to the end. So now I'm going to separate those two into x and y data, xi and yi. And I'm going to call this xi, yi, just to standardize the discussion. So how do I grab this? This input data is a 2-dimensional array, right? And so if you're confused, you're like, okay, what if I do xi0? What does it give me? Or, sorry, data. Input data 0. Input data. And I'm going through the process of like, okay, I forgot how to do this. Okay, input data 0 is going to contain, it's going to be indexed by row. Input data 1 is going to give me the second row, 150 and 2.33. That's not what I want. I want the entire first column, right? So for the entire first column, I can do slicing. I'm going to go give me the entire first column, comma, indexed at 0. That's column 0. And then when I do this, it gives me that first column, right? So what I'm saying here, this is two-dimensional array. For the first index, give me the entire, all of the data indexed at column 0. The next one is going to be indexed at column 1, but also give me everything in column 1. Okay? So that's what I'm doing here. So let's call this xi equal. And then yi is going to be input data. Same thing, but at column 1, at the second column. So if you're in doubt, just print it. Print yi, it gave me those data. Now, one of my students last year came up with another slogan for the class, like when data is at hand, plot it to understand. It was Aaron. He's still an undergrad. Hopefully he'll join our grad program. And so once we have data, let's plot it. plt.plot. I'm going to do xi, yi. Now when you do this, this is bad. Okay, this is not your actual data. Your actual data is only a scatter. Okay, so plot it as a scatter. You don't know how the data are connected together. Okay, if you decide to plot a line in between, I don't think that's the truth, but that's what linear interpolation would look like, right? This is a straight line, this is a straight line, a straight line, a straight line. So I'm doing this just to illustrate what linear interpolation is going to look like. So once we do linear interpolation, we're going to plot some data on this, and you will see that the data is going to fall on these straight lines. It's not going to fall here or here. It's going to fall exactly on that straight line. Okay? We good so far? Let's clean it up a little bit, make it black. So yeah, I put K for black to make it black. Okay. They don't use B for black because B is for blue, RGB. So and then you see the other color profile, CYMK, K is black. So K is referred to as for black. Okay. So now let's say I want to interpolate a single data point. I would like to get the temperature at the density at a temperature of 132. All I have to do, turn this off. Okay. So let's say I want to get the temperature at 132. So somewhere here, I have the temperature at 100, which is this guy. That's from my input data. 200, I want to get it at 132. It should be in between, somewhere over there. And all I have to do is np.interp. Interp, there you go. So this is a one-dimensional linear interpolation for monotonically increasing sample points. So I have to give it x and xp. X is the coordinate at which to evaluate the interpolated value. Xp is the x-coordinate of the input data points, and fp is the values of the input data. So very simply, what I want the value of the density at 132 Fahrenheit, or what is it, Kelvin, 132 K, yes, the temperature is in K, 132 K with Xi and Yi data. And when I press this, it just gives me 2.77528. What are the units of this? They're kilogram per cubic meter. This is the temperature, the density at 132 Kelvin. Kelvin, yep. So is this correct? Yeah, because between 100 and 150, the density goes from 3.55 to 2.33. So my temperature, my density should be in between those, and it is indeed, it's 2.77. That's what I expect it to be. Okay, that's what I expect it to be. Okay. Now let's say I want to do it at a few other points. Let's say so let's formalize this a little bit. I want to compute the density at a few different temperatures. Let's say 132, and then 251, and then 445, and then 602.6, right? Just some bunch of temperatures. What's so cool about interp is it takes a single value or it takes an array. So if I do np.interp, of xe, xi, yi is going to return an array of what? Densities corresponding to those temperatures. So this is the density at 132, density at 251, and so on and so forth. Okay? So let's store them in an array as well. Ye is equal. And let's actually plot them now. So I'm going to plot the original data. Again, data, I'm going to copy this from here. Let's plot the original data. And I'm still connecting it with straight lines because that's what a linear an interpolation to straight line looks like exactly. So what I would expect is that the ye, they lie exactly on those lines, not slightly below, not slightly above, because this is a straight line connecting the points. Okay. Next, we will plot plt.plot, and we're going to do xe and ye, right? The points at which we interpolated. We're going to make them in red squares. All right, so when I do this, there you go. This is my, see, I told you, it's right on that straight line. Whatever I move the temperature here, this red point is going to be always on this straight line because this is interpolation to a straight line. We built a straight line here, and then Python figured out the slope and the intercept and calculated the value of the density at a temperature that's not given to us in the input data. Okay? This is a great way to do interpolation, a great way to calculate values in between data points. Okay, and you can, yes?
If we want to find the temperature from density,
okay.
we need to exchange the...
Yes, so that's going to come next. Yes, thank you. Yes, you're spot on. So I'm going to do that exactly next. Before I do that, I just want to do one more thing that you can also, you see this array of xe and ye, you can put a lin space here to give you just, instead of just having 10 temperature values, you can plot all the way across all of these points. You can plot 100 points here, or you can calculate any number of points in between here, okay? So give it an array at where you want to calculate it and get the value. Okay, very good. Now we will come to, let's say we want to do reverse interpolation. Okay, so we're going to call this reverse interpolation. So what if now I want to actually look at computing the temperature from a given density? So this is a one-to-one data. There's no two values for temperature or two temperatures for a single density. This is one-to-one correspondence. Okay, for every value of temperature, there's a single value of density. And therefore, for each value of density, there is a single value of temperature. We're assuming standard pressure. Okay? So when I tell you the density of air at standard pressure is, whatever, 3.5, then you can tell them the temperature is 100 Kelvin. No questions asked. Vice versa. Okay? And your colleague suggested we swap xi and yi. First, let's just kind of plot a little bit. So plt.plot. I'm going to plot now yi, xi. Okay, and I'm going to make it dash OK. Dash OK. Okay. So now I'm plotting on the x-axis. I'm plotting the density, and the y-axis is the temperature. Okay, we just flip that plot sideways. So now the question is, I am given. So let's rename things. Let's call density equal yi and temperature. That's where xi and yi is a bad idea to use, because what is x, what is y? But if you call them density and temperature, the variables will become a little more intuitive. So when you are trying to reason with them, it's easier to think about this. So let me just kind of rename yi, call it density, and temperature. That was my input data xi. Okay, so now the question is, previously we did interp, we treated.
Sorry, density now is xi, right?
Yeah. No. So initially my data, my input data, I stored the temperature in x and I stored the density in y. I just renaming them. Still, x contains temperatures and y I didn't change. Anything.
I mean,
In the plot, the density is on the x-axis and the temperature is on the y-axis. But here, xi contains temperature values, yi contains density values. I'm just giving them a new name. Okay? So then when I do next, okay, so since you propose this idea, what density do you want to compute the temperature at? 1.9. Okay, so at 1.9, we're just about here. We should expect a temperature just around 200. Agreed? Okay, let's see what happens. Interp. Now, we want it at 1.9. That's my density. Now, my x values are going to be the density, right? Because interp takes x values and y values as in that order. I'm treating the density as my x values and temperature at my y values. Temperature. Okay? Oh, np.interp. The answer is 1,000. No. The answer doesn't make sense. So we expect the temperature at a density of 1.9. The temperature should be around 200. It's giving me 1,000. That's a problem. Okay? That's a problem. Well, the fix is simple. And you have to understand, in this case, the tool that you are using. Okay? So let's go dig a little bit deeper into our tool, which is numpy.interp. And I'm going to press Shift-Tab. This, by the way, is going to be the case for any value of density you put here. It's just going to give you the wrong answer. Okay? Okay. Now, what this does, one-dimensional linear interpolation for monotonically increasing sample points. So the input data that you give to interp have to be monotonically increasing. The x values have to be monotonically increasing. Okay, when we did the interp with the temperature and density, temperature as the x values, temperature was monotonically increasing, 100, 150, 200, 250, and so on, correct? So let me type the temperature so you can, temperature. It's 100, 150, etc. But when we looked at density and treated density as the x values, well, density is not monotonically increasing, it's monotonically decreasing. So to fix this, we have to reorder the density so that it is monotonically increasing. Okay? We have to reorder it, we have to resort the array to do that. Okay? To do this, I need to go back to the slides to explain to you how to do it. So yes, you can use a tool. If something goes wrong, try to read up about the tool. Okay? Because I'm sure there's other things that could go wrong I haven't figured here, or I haven't covered here. So I have a warning here that the abscissae, or the xi's, they need to be sorted in increasing order. Okay? There are three ways to deal with sorting. There's a very general way, and there are some very specific ways. So in our case, the density was monotonically decreasing. All I have to do is flip it so that it becomes monotonically increasing. But don't forget to also flip the temperature. And also the temperature was monotonically increasing. So if I flip it upside down, this is called flip UD, flip upside down. So I can do this in this particular case. This is not the general or best approach, but it works for this problem. So now, new temp is temperature, or np dot flip upside down of temperature. So now when I print new temperature, it's going to be, it's flipped. Okay, because now I'm treating my temperature as my y values, because I'm looking for making sure that the density is monotonically increasing. So new density is equal np dot flip upside down of density. And then I can print new density, and it's going to be monotonically increasing, 0.3 all the way to 3.5. Why did I need to also flip the temperature? Exactly, because they need to be one-to-one connection. I cannot keep the temperature from 100 to 1000, but flip the density, you get the wrong values, right? So I have to maintain the order. I have to flip all of the data together. Now, in this case, let's try it. So I'm going to go back and copy this, put it here. But here I'm going to have new density, new temperature. Oh, look at that. Perfect. 187 Kelvin. Yeah. So when something goes wrong, don't assume you're wrong because you're always right. When something goes wrong, try to look at what you might have a bug in the code, or you're using it wrong. And it could be both. That's the hardest to figure out. Okay, so get another set of eyes to look at your code, for example, but then look at the signature of the tool that you're using. How do you use it correctly? Okay? In general, though, the best way to do this for data that's, so what if my temperature and density were scrambled? I had 100 temperature 100 and then 500 and then 350, and it's not ordered at all. You have to sort it either by increasing or decreasing order. The cleanest way to do it is with something called arg sort or argument sort. So this is a routine from NumPy. It gives you the indices of the array that would sort the array. It gives you the indices of the array that would sort the array. Now, the way you use it is mind-blowing. The best way to do it is by example. Okay? So I'm going to give an example. Simplicity. A is mp.array. And let's put 5. And let's put 1. And then 10.8. And then 0.1, 0.2. And then, OK, let's keep it at this. So we have actually 5. Let's do 7, 1, 10.8, 0.1. Now, the indexing of this array, this is at index 0, index 1, index 2, index 3, index 4, index 5. So 0, 1, 2, 3, sorry. Index 0, index 1, index 2, index 3, index 4. To sort this array from small to large, monotonically increasing, it has to be 0.1, and then 1, and then 5, and then 7, and then 10.8. Agreed? So the indices should be 4, and then 2, and then 0, and then 1, and then 3. So argsort gives you that indexing that would sort the array. If I were to do mp.argsort A, it's going to give me an array of indices that would sort this array A. See, these indices this array, if it were sorted, monotonically increasing, it would start with index 4, which is 0.1, followed by index 2, which is 1, followed by index 0, which is 5, followed by index 1, which is 7, followed by index 3, which is 10.8. How do I cache this? What do I do with these indices? This is so powerful. So let's call this IDX sorted, or sorted indices. Okay. All I have to do is say A IDX sorted. Check this out. Insanely beautiful. So I got the indices that would sort the array A. To get the sorted array, I just apply the sorted indices to A, and it gives me the proper sorting. This is generic. Okay? This is generic. Now, when you have two arrays, temperature and density, you sort the one that you need to sort. You don't sort the other one with argsort. No. You take the indices and apply them to the other array so that you still have one-to-one connection. Okay? Give you an example. let's say we keep my A here, array. Let's create a B. Say that's my Y values, and it's also an numpy.array that I need to know to make sure that 5 corresponds to 1. Let's say, or okay, let me do it this way. 1.5, 1. So 5 corresponds to 1.5, 7 corresponds to 1.7, 1 corresponds to 1.1, 10 corresponds to 1.108, and 0.1 corresponds to 1.01. Okay, just to remember the correspondence, okay? So this is my Y values, this is my X values. I want to sort my X values, I already did. How do I get the corresponding sorting for the Y values? I should have 1.01, 1.1, 1.5, agreed? So what I do, I don't sort the B array, I just use the indices. B, ID, X, sorted. Oops. B is not defined, of course. Okay, there you go. I didn't have to sort the B array, but I had to rearrange it so that it matches my X values. Be careful, yeah? So just sort the array that you care about, and then use the indexing to apply it on the Y or dependent variables. Okay. In general, you can also interpolate to a to a polynomial, to a generalized polynomial. The challenge, though, there are many issues when interpolating to a polynomial is that when you take an entire data set, your order of the polynomial needs to be very, very large, especially if you have a large data set. In general, for n plus 1 data points, you can fit a polynomial of order n. What's a general polynomial? A0 plus a1x plus a2x squared plus a3x cubed, and so on and so forth, right? So that's a general polynomial. So when you have n plus 1 data points, you can fit a general polynomial of order n at most, okay? And you might say, well, polynomials are going to be a better interpolants. Sure, but not really. Only locally, and we'll understand why. Remember, an interpolant by definition must go through each and every point, so that polynomial, you know, for example, if you had, 10 data points, you're going to fit a polynomial of order 9. So that polynomial is going to have x to the power 9 in it. Okay, so let's see what happens when that's the case. So to do this in Python, we cannot use interp. Remember, interp was limited specifically to interpolation to a straight line, ax plus b, straight line. When you want to do a general polynomial, a0 plus a1x plus a2x squared, and so on, just a general polynomial, you have to use what's called polyfit. I need polyfit to do regression as well, so it's a good thing we're talking about it. Polyfit takes at a minimum 3 arguments and returns something. And it's also coming from NumPy. Okay? The xi data are your input, x data, same thing as interp. Your yi data are going to be your, dependent input data, so density temperature or temperature density. Your degree is the order of the polynomial you're trying to fit. That's the number you put in. For interpolation, degree needs to be equal to the number of data points minus 1. For interpolation. If you do anything less, it becomes regression. We're going to talk about this later. So if you had 50 data points, if you put degree, you have to get polynomial interpolation, you have to put degree 49. So you get the length of the data points minus 1, very simply. If you put degree equal 2 or 3 or 5, that becomes regression. It's a different question. For interpolation, degree needs to be equal to the number of data points minus 1. In other words, for n plus 1 data points, degree is equal to n. For n data points, degree is n minus 1. Coefficients is what is returned. It's what polyval returns is an array. I store it here in a variable called coefs. It's the array of coefficients of the polynomial in this order, starting with the highest degree coefficient to the lowest degree. So it's going to give you the first entry in coefs is going to be an, the coefficient of x to the power n, and so on and so forth, all the way to a naught, which is the coefficient that doesn't multiply any x value. Okay? That gives you, that's how you build the interpolation. So this only gives you the coefficients of the polynomial. Next, you have to take, to do interpolation, you have to take these coefficients and actually write a routine doing coef a0 plus a1x plus a2x squared and so on, and put in the x value to compute an interpolated value. Well, Python, they also have a feature to do this for you. Once you know the coefficients, you can use something called polyval. Polyval is a polynomial evaluator routine. It takes a bunch of coefficients for a polynomial in the order that polyfit gives you, an to a0, the coefficient of the highest power, all the way to the coefficient of the 0th power. And you're trying to evaluate or interpolate data at xe, so it could be your temperature, your density, whatever, and it's going to return a value, the interpolated value for you. Okay? So that's all you need for these two. There's another way you can also, make sure the coefs belongs here, and you have xe and ye as your input and return value. All right, so let's do this now with our data and see if this makes sense. Right, so now using a polynomial, interpolation to a polynomial. So I need to do, this goes like this, coefs equal mp.polyfit, and polyfit takes at the minimum x, y, and degree. It's got a bunch of information. It tells you here this is a least squares polynomial fit, but be careful, degree of the fitting polynomial. If you read the full discussion over here, this is actually an interpolant. This is actually an interpolant that interpolates to a polynomial of degree. If you have n data points, the degree is n minus 1. Okay? So let's take again our temperature as our x values, okay, and then our density as our y values. And then for this to be an interpolant, I need to have degree equal what? It's the length of my data, so len temperature, minus 1. Just for the sake of understanding what's going on, let's see, len temperature. So I have 19 data points. This is going to be a polynomial of degree 18. So it's going to have 19 terms, a0 plus a1x, etc., plus a18 times x to the power 18. So when I do this, it's going to give me a warning here. Polyfit may be poorly conditioned. Disregard that for a second. But let's print coefs. Coefs contains numbers. They correspond to the coefficients of the polynomial. Fit this polynomial that fits all the data, temperature, and density, looks like minus 7.42 plus 35.8x minus 0.771x squared plus 9.8 times 10 to the minus 3 x cubed, and so on, all the way to 5.8 times 10 to the minus 46 x to the power 18. Okay, x to the power 18. Now you will notice that these coefficients get incredibly small as x becomes incredibly large. X to the power 18, if you put 1.1 to the power 18, that's a very large number. And it has to be multiplied by a very small number so that you get a reasonable value. All right? This warning comes from this fact because there's a lot of round-off issues going on here. But there's also other issues that we will discover together. Let's first try and see if we can actually get any values from this. Okay, so let's call polyval. So let's say compute the density at 412 and 415. Okay, so if I go back to my plot here, 412 should be somewhere here, and 415 as well. Should be within this range between, maybe 0.8 and 1. So let's see if it gives me okay values. I'm going to do np.polyval. So evaluate a polynomial at a specific value. Okay, and then P is an array-like of polynomial coefficients, right? An array, 1D array of polynomial coefficients. So that's my coefs over here. And I want to compute at 412 and 415. It's going to give me two values of the density. Okay, that's what I expected, somewhere between 0.8 and 1. 0.847 at 412 and 0.841 at 415. It's consistent. As the temperature increases, density is going to decrease. Okay, it's good. That's great so far. Okay. Now, what if I want to do at, let's say I want to do it at 980. Okay, like right here. At 1000, the density was around 0.5. 950, it was somewhere here, maybe 0.6. So let's do it at 980. So np.polyval coefs at 980. Mine is 0.4. Can you have negative density? Nope, not in this universe. Something is wrong. Okay? But how come? How come it's wrong? The polynomial should go through each of those values, right? Even if it's an 18th degree polynomial. So let's try polyval at 1000. Let's try polyval at 1000. It gave me 0.34. It's the correct value. What the heck is going on? What do you think is going on? Give me a hypothesis. If you know the answer because you took my course before, don't answer. Yeah.
Well, we just required to go through each of the points, but we don't necessarily define like a good curve fit on there. So it might be doing a huge amount of bounces, but happening in each of the points.
In between the points,
yeah.
Right? And why do you think this is okay? So your colleague is saying that we only said that the polynomial has to go through the input points. We didn't say anything about how it's going to behave in between those points. Now, why is this particularly an issue for high-order polynomials? How many roots does a polynomial of order 1 have? So a straight line, how many roots does it have? How many times does it cross the x-axis? 1. How many roots does a quadratic have? 2. How many roots does a cubic have? How many roots does an 18th order polynomial have? 18. What does a root mean? The polynomial has to cross what? The x-axis. So it's going to have to change sign. So this 18th order polynomial is trying so hard to change signs 18 times. Maybe if you're lucky, it's not going to change sign in those points that you gave it. But in this case, it did. How can we see this? Let's actually plot that darn polynomial. So what I'm going to do, I'm going to create a lot of points. I'm going to say a lot of temperature points. Temp points. I'm going to create an np.linspace. From 100 to 1000, I'm going to put 200 points. So I'm going to create an array of temperatures from the minimum temperature to the maximum. I'm going to put 200 points, and I'm going to evaluate my polynomial at all of those points to see how it's behaving. If I plot my polynomial at the input points, it's going to look like the input points. That's why you shouldn't connect it with lines. So let's do this actually first. Let's plot at our polynomial, plt.plot, polyval, coefs. Okay, let's put the, so we have where xi or temperature, those are the temperature values, right? So if you print temperature, these are the temperature values. So I'm going to plot my polynomial only at those temperature values. Polyval, coefs, temperature. Agreed? So it's going to return to me the polynomial value that the polynomial interpolant at those temperature values. Okay, when I plot this, np.polyval, it's going to look normal. Then I can do OK dash. It's going to look normal. But that's why it's a bad idea to connect it with lines, because this is giving you the impression that your polynomial is well behaved here. But it's not. I only plotted it here, and I fictitiously connected it with a line, which you shouldn't. To do this correctly, let's create a very dense lint space. I'm going to put 300 points. And then plt.plot temperature points and np.polyval at those coefs and at those temperature points. And I'm going to do just a dashed line, okay, because it's going to be a lot of scatter. Ha! That's what my true polynomial looks like. You see there's a little kink up here, and there's this huge dip where it goes negative below 0 right at the end. Now I have a lot of points here, so I have the right to connect them with a line because it's 300 points, a lot of points. So then you can see the curve. This is the true polynomial. This is misleading. Don't connect your data if it's discrete and sparse, not too many data points. Don't connect them with lines. Gives you the impression that things are okay, but things are not okay. This is not okay, what's going on. What it did here, the polynomial was like, oh, I want a root, I want a root. It hit two roots here. It went down, this is a root, it went up again. It's another root. That's a problem with all high order polynomials, even order 4 and up. They want to get roots, they get highly oscillatory. Where? At the endpoints, always. We never interpolate with high order polynomials. So why did I get you through this exercise? To teach you polyfit, because we're going to use it for regression, okay? But it also teach you the pitfall of doing this as well. Am I done? Yes, no? Yes, I'm done. Okay. Thank you, Godspeed. I'll see you on Thursday.